let's look at another problem that we have. Now, in one of the basic constructions that you have to be able to do in all of geometry is to call the problem is to say to square a figure. And what that means is to say, can you take the area of some figure that you're given and create a square with exactly the same area? This is a very useful construction because it enables us to then do other problems that are interesting. So the question is, can we square a rectangle? And so basically what we're saying is, in picture form, give me a rectangle that looks like this. Can I produce a square so that the area of this square is exactly the same as the rectangle? And let's take a look at how we can do this. So what I'm going to do is I'm going to begin by labeling this with little a and little b, two sides of my rectangle. So I have rectangle AB, and the question is, can I construct a square of equal area? So what I'm going to do is I'm going to begin with a segment. And here's my segment. And what I'm going to do with this segment now is I'm going to put a point on it right there. And this point is a point that can move back and forth but can't jump off of it. It has to stay right there. The next thing I'm going to do is I'm going to construct the midpoint of my segment. And now I'm going to go from midpoint to end, and I'm going to construct a circle. You're probably wondering why I wanted to do this. Well, I need the circle to help me set up the problem, as it were. And I'm now going to hide this point right here because I don't need the midpoint anymore. Now, so this is going to run around. Now, what's going to happen here is I'm going to think of this little segment right here as A and this segment over here as B. So there's my A times B. So another way of looking at this is, let's look at the rectangle. So I'm going to create, by construction, a perpendicular. And now I'm going to take a circle and I'm going to swing it down. And when I say swing down, what I'm doing is I'm swinging this length here down to right there, because I know all the radii of a circle are exactly the same length. So now I'm going to hide this circle, and now I'm going to create another perpendicular. Now by doing this, I now have one side, two sides, almost the third side of my rectangle. So over here, I know I need another perpendicular because that gives me my right angles. And lo and behold, I now have a rectangle. So in order to see just the rectangle, let me throw up some segments, and only some segments. And I'll start hiding some lines here in just a moment. And I'm going to leave this line right here just for a moment, but I'm going to put in the interior of my rectangle so we can really see it. And I'm going to measure this area. And there we go. Now, this area I claim is the same as saying this distance from here to here. I will measure. And I'm going to measure the distance from A on to D. And if I were to go and do a number calculation, and I were to say take the first one times the second one, it is in fact my rectangle, no matter where I put A or how I split up the A and the B. All right. Now the question is, how in the world do I create, construct, determine where it lives, a square that has this area that I've been given? Well, let's watch where it is, because it's right in front of us. We're just not looking at it yet. You see this little segment right here that goes up to the circle? Well, what we want to do is get the intersection. Now there are two of them, but I'm only going to focus on this one right here. This little point right there is going to tell me everything I need to know. So I'm going to take that point and this line, and I'm going to construct a perpendicular. Now I'm going to take this as a center, this as a point, and I'm going to construct a circle because that's my way of saying give me the same distance in a different direction. Therefore, I can now hide this circle because I have this point over here and this line, and I'm now going to construct a perpendicular coming down onto my diameter, as it were. And I'm now ready to create another interior. Let's watch this interior. And we're going to measure it. And lo and behold, we know it's a square, and we know it has the exact same area as the rectangle. To square a rectangle. Now think about what this is telling us, though, in another way. Because sometimes we don't think about these things. You're thinking about the geometry. We still do this very problem. Notice E to A we said was a length called A. Then from A on to D we said was a length B. And we said A times B gave us a rectangle, and we said that rectangle just gave us that square, and that square has a measurement from A up to F. Call that H squared. So notice what we've actually said here. We have A times B is H squared. So that means that if I were to make that equal to 1 and called it unit and measured everything in terms of it, this problem becomes B equals H squared, which means I know the square root of B is the height of H. It's a methodology for constructing square roots. You just have to let one of your lengths become unity, that by which you measure. Also, it's kind of interesting in the fact that when we look at this, it also means we have a couple of right triangles up here that we need to investigate. Let's take a look. And permit me, I'm about to hide a whole bunch of stuff. And I'm going to hide this piece because I don't need it. But I do want to look at this triangle, and this triangle, and the big triangle, of course. So now, let's look at this little right triangle here, and this triangle right here. Now, those two right triangles are similar. And the reason is, look at the big triangle, E, F to D. Well, EFD is similar to triangle, and let's see, we went up a short side and a long side. E, A, F. And the reason is two angles in these two triangles are the same. Namely, the angle at E is in common to both of them, and both of them are right triangles. Also, we know EFD must be the same as this triangle right here, which we're going to do, and what do we say? Short side, FAD. And the reason is D is common to both this triangle and the above triangle, and a right angle. Angle symmetry is given to us. So these three triangles are all similar to one another. And that's where we get a nice formula which says, hey, I can take the short side to long side, A over H is equal to H over b, short side, long side, and that's where I get a times b equals h squared, which we had over here. So we see how the Greeks were approaching all of their mathematics through the use of geometry and proving beyond a doubt with rigorous logic that these findings must make sense. And because of this, the Greeks, we credit them with being the fathers of the way we think in the world today. The Greek tradition, where logic must be present, not just examples, but generalizable findings. This is why you do proofs in math classes today. It's the Greeks' fault if you want to blame them. They gave you both a blessing and a curse. I hope this helps.